We're discussing connectedness and path connectedness, and there was one counter example where we had a subset E contained in F, contained in E closure, and of course E is connected, E is path connected, so of course it is connected. So E is path connected. We had an example. Okay, we saw an example where E is path connected. This implies, of course, E closure is all E closure F are connected. And in fact, you can see that E closure is path connected. In the earlier example, we saw E closure is path connected, but this F is not path connected. Of course, if E is path connected, E closure and any set containing E contained in E closure, they are all connected. Okay, but then F is not path connected. We saw this example the last class. So now we will see another example, which is where E closure, E is path connected, E closure is not path connected. So let's E equal to all those X sine 1 by X. This is a standard example. X in one side half open, close one side, I mean half open, half closed interval. Okay, like this. Then E closure is all those things. E union this set 0 cross minus 1 1. Okay, it's something like this. We have minus 1 here. It will go like this, but then it near 0, minus 1 to 1, it will have all the, because it's sine 1 by x will go to infinity. So it will have all possible values and you will get everything. So you can prove that E closure is this very easily, because if it is not 0, it will be somewhere. You can prove it's there. If the x coordinate is 0, then that has to, we will get all the values. Okay, that's easy to prove. So, okay. So, okay. Now we want to prove that E, so E is, of course, E is just a path. So E is clearly path connected. Okay? E is path connected. And of course, this means E closure are connected. Okay, so we want to prove that E closure is not path connected. Okay? So suppose if it is connected, suppose E closure is path connected. And suppose there exists, that is, there, I mean, and there is a path. Suppose there is, I mean, rather than path connected, suppose there is a path connecting 0 0 and 0 1. Okay, let k equal to, there is no k this time, k equal to there is a path gamma connecting these two, at k equal to gamma inverse of this set 0 cross minus 1 1. Okay, then k is closed, k is clearly closed and k is compact. Okay, zero zero. What? What 1 0? 0 0 and 0 0 0 0 only corrected. Why? 0 0 and 1, sorry, 1 0. Okay. 1 comma 0, yeah, sorry. 1 comma 0 is sine 1, sorry. Yeah. Sorry, I was having the earlier example. Okay. Yeah, this is okay. 1 comma sine 1. Okay. I mean, we just need something in E and something in this y axis. What 1 by pi? 0 comma? What is 0 comma 7? Where is 0 comma 7? I just want this point and this point, which is, I mean, this is 1 0, no? Yeah, this is 1 0. I mean, this point is 1 0, so yeah, the point in that, okay? In this point, okay? Okay. So as before, let T naught equal to supremum of E in K, supremum of K. Okay? Supremum of, yeah, this is something contained, compact set contained in 0, 1. Okay? So you take T naught to be supremum of K. Okay? So then, of course, T naught is in K because it's a compact set. T naught has to be in K. Okay? And by this condition, this is a supremum for all T greater than T naught, gamma of T cannot be, is not contained in this set, so it has to be in E. Okay? Okay? So now you just take, I mean, now you take T naught and slightly increase it by delta or something. Okay? So gamma of T naught, you project it onto the x-axis. This is the projection onto the x-axis. Okay? Gamma of T naught. This is a continuous function. Projection is a continuous function. So this is equal to 0. T naught, I mean, gamma of T naught is in, I mean, Px of gamma of T naught is 0. Okay? Because it is in that 0 cross -1 -1. Okay? This is equal to 0. And Px of any gamma of T naught, let's say some 1 by K, okay, is greater than, I mean, it's going to be in that, it's going to be greater than 0. Supremum of all those elements in K. Supremum of all T such that T is in K. Okay? K is a subset of 0, 1. Okay? Supremum of a compact set. I mean, compact set is contained in real line, then you can take supremum. Supremum of all those elements in K, it's a subset of real line, so you can take the supremum. Then that supremum is in K. Okay? So because that is in K, it satisfies this condition. So gamma of T naught, I mean, gamma of T naught should be in that I mean, in this set. So its x coordinate should be 0. That is what Px is the x coordinate. Okay. So Px of gamma of T naught is 0. Okay. But if you slightly increase it, it will not be in that set. So of any T naught plus 1 by K is strictly greater than 0. Okay. So there exists Nk. Actually, I can take any point there. I need not even take a path connecting 0, 0. I can take, there exists Nk. Okay. Now I am taking 0. Okay. There exists Nk such that Px of gamma of T naught plus 1 by 4, 2, I mean 2 Nk pi 2 Nk plus half pi. Okay. Some Nk. For each K, there exists a Nk. Okay. This is increasing to, I mean, that's right, no? Yeah. No, it is just some Nk, 2 Nk pi. I mean, x goes to 0. Okay. So 1 by, there exists something, some Nk for this is less than that. Okay, such that 1 by 2 Nk plus half pi is less than that 1 by K. Okay. Okay. Huh? That was just a line, sorry. Yeah, it's not debug. Okay. So now we are done, I think. Now Py of gamma of T0 is 0. Okay. And the Py of this Py of gamma of T0 plus 1 by that 2 nk plus half times pi is going to be 1, right? 1, which will be what was the problem? P sine. No, sorry. I have to use intermediate value theorem. I'm sorry. Yes. No, sorry. I'm sorry. No, it was. Sorry. I have to use intermediate value theorem. Px of this is 0. Okay. And Px of gamma T0 plus 1 by k is greater than 0. And this interval T0 plus 1 by k is connected. Okay. This is an interval. Okay. This is connected. So there exists a tk in this T0 plus 1 by k. Okay. Such that uh, so gamma px of again the same thing. I mean, I'm applying for this continuous function. Px of gamma is a continuous function, and Px of gamma, I mean Px, I'm taking f to be Px of gamma. Px of gamma acting on T0 is 0. Px of gamma at this point is greater than 0. So there exists a tk in this interval such that Px of gamma of this tk is equal to that number, whatever that number I want, 1 by, I mean, which is as small as we want. So which is equal to 1 to, I mean, 2 nk plus half. Right. This is okay. There exists a, I mean, for this key tk, there exists a nk. There exists tk so that, I mean, some nk. Okay. This is okay. There exists a tk and nk. You take this value. Is this okay? You tell me. Huh? I'm in the right person. Yeah. For, no. See, you have T0 plus 1k. Okay. After some time, there exists a nk. This will be in this interval. There will be some nk such that this will be in this interval, right? Okay. For that nk, there is a tk. Okay. Okay. I mean, and you. Okay. I mean, this is between 0 and this number. Nk is some. I mean, nk is such that this is 1 by 2 nk plus half pi is less than this number, Px of gamma of T0 plus 1 by k, T0 plus 1 by k greater than 0. Okay. This is a number greater than 0. This is 0. And for some nk, this is between these two numbers. By intermediate value theorem, by intermediate, this is by intermediate value theorem. Let me write it and then explain. I'm sorry for the confusion. It's very easy, but where the maybe I'll erase it. Shall I erase it and write? It's okay. It's clear now. I think it's clear, but maybe the way I said is confusing, but I can explain you clearly. Okay. So this Px of gamma T naught is 0. Okay. Px of gamma T naught plus some 1 by k for any k is greater than 0. So there exists some nk such that this number, whatever this number is between Px of this and this 0. By intermediate value theorem, there exists a tk here such that this happens. So this thing follows by intermediate value theorem. Intermediate value theorem. Okay. I hope it's clear. Okay. Now we are done. This is just bigger than 0. This is something close to 0. There should be something, no, some nk, which should happen like that. Okay. Yeah. Okay. And we have, so then this, so as tk goes to t naught. Okay. That's clear because 1 by k goes to 0. Tk goes to t naught. And all these things, px of gamma of that tk, which will be sine of 1 by that, which is just 1. 2. What? T? Py, sorry. This is py. Py, correct. Yeah, this is py of gamma of tk is 1. Okay. But that has to be 0 there. It does not converge to 0. That's all. This is a contradiction. So it's not path connected. Why I can get confused? Is okay? I mean, it's similar to the same, I mean, similar to the earlier proof. You can actually do this by considering the infimum and the other E, taking the infimum, but the infimum will not attain here, it will attain in this set, and you can do the same thing with that also. It will work. But I don't want to do that now. I'm getting confused. Okay. So these are examples which are, I mean, sets which are connected but not path connected. Yeah. Why is py of py? I mean, the gamma of t0 or t0 is not 0. You are right. That's right. You are right. But then py of okay. Then I can take this to be some number. I mean, 1 second. 2nk. You are right. Actually, this is because plus theta. For any theta, this will work. Okay. This is okay. For any theta, this will work. Then this will be equal to sine theta, right? Where is it? Py of this is equal to sine theta. Okay. But then you can take any theta for this works. Okay. But then this py of gamma of t0 is some sine theta naught, something, okay, which will not. There is no reason why sine theta should converge to sine theta. Now it's okay? Huh? Yeah. I'm sorry. Yeah, earlier I had, I mean, I thought that is also 0, but yeah, that can be, I mean, for t0, it will lie in this. Okay. So if py of gamma, this is some sine theta 0, and this is some theta, then yeah, this will go. You can work it out. Okay. Okay. Another example. This is a connected example. You have seen that GL and R, all those matrices A, M and R, such that A is invertible. Okay, A is invertible. You know, this is not connected. Okay. Connected because this function determinant from GL and R to R, this will, I mean, if it is connected, then the range of this should be connected, but that will be minus infinity 0 union 0 infinity, which is not connected. The range of this is a range of determinant is this. Okay. I mean, suppose if it is connected, then the determinant is a continuous function, which is just polynomials in, I mean, in n variable. So range of this should be this, where this is this. This has to be connected, which is not the case. So this is not true. On the other hand, this is connected. GL and C, all A in M and C. Huh? This range, which range? Why is it R2 minus 0? You mean C minus 0? But that doesn't prove it. That doesn't prove it. That doesn't say this will not work. That's all. Yeah. Okay. The A is invertible. Okay, so we want to prove that this is okay. But then this is equal to all those A in M and C such that determinant of A equals 0. Okay. So not equal to 0. Okay. Okay. So I mean this is GLC is connected. That's what we want to prove. Okay. So if you prove the following lemma, this will be proved. Okay. Which says that Cn minus, so P is a polynomial. Is a complex polynomial in n complex variable. Okay. And let Z of P equal to all those P of Z1 up to Zn, all those Z1 up to Zn in Cn such that P of Z1 up to Zn equals 0. Okay. All the zeros of P. Okay. I mean, if you have complex polynomials, even in two variables, the zeros can be, someone decrease the AC, someone increase the AC. Is someone feeling very cold? Why do you increase to 30? I mean, and I always see it in 30. So, we did not do that. That is someone. No, can you just decrease it, put it at some 25 or something? It's very hot. Yeah. Mm. Eh? Yeah. But here it's very hot. Okay. I have not even a fan. Mm. Okay. So if we have a complex, so all my confusion is because of that. Okay. Okay. So if you have a complex polynomial, okay, then you define the zeros of P, all those Z1 up to Zn where the polynomial is 0, then Cn. So, I mean, the remark is, if you have a polynomial, complex polynomial in more than one variable, then the zeros can be uncountable. It need not be finite. Usually it's finite, right? If you have a polynomial in one variable, complex polynomial in one variable, the zeros are the roots of the polynomial is finite. It's a finite set. Okay, that you know. Of course, in real, even roots may not exist. But if you allow complex number, the root will exist always because as you see is algebraically complete and the number of roots of a polynomial is a finite set. But even if you have two complex variable, then the roots can be it can be uncountable. Okay, it can be 0 on an uncountable set. Okay. So that is why this is important. Otherwise, we already know that if you have a finite set or even if you have remove a countable set, Cn minus a countable set is path connected. But here, if you have roots of the polynomial, then Zp is path connected. Okay. Cn minus roots of a single polynomial, which may, I mean, polynomial in n variable, so is path connected. Okay, the set can be possibly uncountable. Okay. So if we prove this, then this is proved. Because determinant is a polynomial. Huh? Oh, no. It is path connected. You are just subtracting from from Rn square, R2n. What R2n? R2n square. Determinant is a polynomial. Is in the polynomial of the coordinates, right? It is one single polynomial. Yeah, that's what I said. C to the power? It can be C to the power 2n. I don't understand. Cn square. N is arbitrary. Yeah, so what? The lemma is true for all n. Yeah. Yeah, gamma is true for, I mean, n is arbitrary. No, no. This says that Cn minus zeros of a polynomial, one polynomial P is path connected. Okay. Determinant is a polynomial, single polynomial. No, 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 no. It is a polynomial of the entries. There is only one polynomial. For each determinant, you will get a number. Okay? The polynomial is one polynomial. It is a polynomial in the entries. It's a, okay, except the number of variables is n square. No, no, n square. This is also complex. This is also complex. This is only for complex variable. This is okay. So if I prove the lemma, this is proved. Okay, except you need n square there. Okay. Huh? Okay. So proof of the lemma. So let some z in Cn minus z of p, where p is a polynomial in n variable. Okay, and we want to get a path from zw to w tilde, z tilde to w tilde. Let this is not the path. Let me just define gamma z for equal to z tilde plus 1 minus z w tilde for z in C. Okay. This is a function, continuous function. This is not a line. The reason I am taking C is if you take 0, 1 or R will not be path connected if you remove point. But here you can remove something and it will still be path connected because C is isomorphic to R2 topologically. So then P of gamma of Z, okay, is a polynomial in one variable. In one variable. One variable. Okay. Z is in complex. Yeah, this is just different. It's a continuous function. Okay. This is just a linear function. This is not the path. Okay. Then P of gamma of Z, gamma of this is just a linear function. If you compose, if you substitute P of gamma of Z is a, I mean, gamma is a function from C to Cn. Okay. Okay. C to Cn, which takes any Z to this vector, Cn vector. Okay. Then if you, this is just one variable, gamma of Z takes it to gets it to n variable, then you compose with the polynomial, you will get a polynomial in one variable. So the Z of this P of gamma, which is contained in C, is a finite set. Okay. Okay. Hence path connected. Okay. This is a path connected subset, paths connected subset of C. Okay. Now gamma of P of gamma of Z of P of, I mean, I'm sorry, you can call it one single set if you want, but this is contained in Z of P, of course, right? So gamma of C minus this set, okay? Gamma of Z of P of gamma, okay? This is contained in Cn minus Z of P, okay? Okay, now continuous image, gamma is continuous. I haven't said that, but continuous image of path connected set is path connected. You can just compose the path, right? This is okay. If you have a continuous function, S is path connected. And if you have a continuous function and take f of s, if you have f of x, f of y, two things. If you have a path between x and y in S, then I mean, if gamma is that path, then compose the gamma with f, that will give you a path between f of x and f of y. Okay, so continuous image of path connected set is path connected. Okay, so this is path connected. Okay, so this is path connected. So this is path connected. So this contained in this path connected. Okay, This is path connected. Okay. Yeah. Yeah.
The zero set of P compose gamma.
Yeah.
It's a polynomial in one variable.
Correct.
The zero set is finite. The polynomial might vanish.
Polynomial might
vanish. As in, it might be the zero polynomial.
It might be the zero polynomial.
The zero set is that.
Now, why does it vanish?
I mean, if P composed with gamma is the zero polynomial. That was because P to be the zero polynomial.
Yeah.
C minus zero set is path.
See, I mean, you are saying that Z of
Maybe just need that P minus that.
no. There are 2 points Z tilde and omega tilde. Okay, which is not in the zero set. Okay, gamma of C contains those 2 points Z tilde and omega tilde, where it is not zero. So it's not zero. Okay, it's not a zero polynomial.
Path connected. Yeah.
No. If you remove the zero set, that is path connected.
So it is minus Z of.
Yeah. No. Hence path connected. This is equal to a finite set. Hence that is path connected. I orally said it, but I didn't say that. Hence C minus Z of P of gamma is path connected. Okay. I mean, I define this gamma like this, which is a linear function. I compose with P of gamma, which is a polynomial in one variable. So the zero set is finite. It's not everything, because at it takes the value at 1, it takes the value Z tilde. Sorry, at 1 it takes the value Z tilde. At 0 at 0 it takes the value W tilde. So which are not 0. So it's not a zero polynomial. And C minus this is path connected. Now gamma of that set is also path connected because it's a continuous function. Gamma of this is contained in this, right? Because the only place where that polynomial can become 0, okay, gamma of this is contained here. Okay, now this W tilde and Z tilde are in this set, gamma of C minus Z P of gamma. So there exists a path. That's all. So that's all. That's what we want. We don't, I mean, we want to prove the whole thing is path connected. We just pick 2 points. We have to prove there exists a path between them. And that is contained in some path connected set. That is enough. Is okay? Huh? Here. You want me to explain? So this is okay. Okay. So you have the zero set. This is path connected. So the image of the path connected set is path connected. Okay. So that is this set is path connected. But this set, I mean, now zero of this polynomial has supposed to be here, right? Gamma of this zero polynomial has to be here. I mean, right? Gamma will land you in Cn. Okay. On this, the P vanishes. So it has to be here by definition. This is 0 of P. It need not be equal to that. It will be a subset of this. Okay. Because of this minus this, I mean, here it will not vanish. Okay. So it cannot be here. Cannot be here. So it has to be continuous image of path connected set is X comma. Yeah, but that E closure is path connected. This is path connected. Huh? Have proven what? Proven what? I just said some time back. If you want image of path connected set, if you want, you take two f of x, f of y there, compose it with the original path between x and y, that will give you a new path. Okay? It's very easy, so I didn't say. Okay? It's okay.
Why is your gamma of that polynomial?
It's defined like that. Gamma is this. If you compose it with P, this is Z tilde and W tilde are fixed numbers. Z tilde and W tilde are fixed numbers. Here it's a function of z. P of gamma of z is a function of z. It's a function of one variable, so it's a polynomial of one. I mean, it's not a polynomial of one variable. It's a polynomial is what you have to verify, which is clear. You are just composing with a linear function, so it's to be polynomial. Okay. Yeah, this is fine. I think we will stop connectedness, path connectedness with this. We are going to do more, but that is a set which is totally disconnected, which is the Cantor set. We will discuss Cantor set in this. Okay. Okay. So I have some half an hour. Because of the confusion and because that was not working, some time was wasted. I did not. Okay, so this is some new topic. Okay, this is this Cantor set. This is just an example. Okay. You take C0 to be that interval 0, 1. This is the Cantor set. Cantor set as more generalization. This is the fundamental example. Okay. There are more generalized Cantor sets and other things. We are not going to talk about that. We are going to talk about this fundamental example, Cantor set in real line. Okay. C0 equal to 0, 1. Then you take C1, you just remove, you divide this 0, 1 into 3 intervals, equal parts, remove the middle interval. Okay. This is equal to, you take the closed interval, 1 by 3 union, 2 by 3, 1. You can write 3 by 3 if you want. Okay. Then C2 equal to 0, 1 by 9, union, 2 by 9, 3 by 9, and then this union 2 by 9, 2 by 9, 3 by 9. This is right. Huh? Yeah. Sorry. This should be 4. No, you have to multiply by 3. So 6 by 9, 7 by 9, union 8 by 9, 9 by 9, which is 1. Okay. So you divide this into 3 intervals and remove the middle part. Divide this into 3 parts and remove the 3 equal parts and remove the middle part. Do the same thing here. Okay. Do the same thing here. Okay. Yeah. No, you just argue it this way. This is contained in this. If you have any 0 here, 0 of this, okay, gamma of this is, that should be somewhere here. That is okay. Now, gamma of this, something which does not vanish here, it will not be somewhere here. It will not vanish here. Gamma of anything which is not here, it will not vanish here. I am not taking complement. You go through the definition. Yeah. Forget about complement. You just here, if you P does not vanish. So the image, I mean, here, if you apply with P of gamma on this, it will not vanish. That is precisely this. Okay. Okay. Return to Cantor set. Okay. So you are taking this interval and you are taking you each time you take that interval, divide it into 3 parts and remove the middle part. So suppose Cn equal to, this may not be some I in I. I mean, this I may not be numbered like that for some I. Okay, I in In. In is some set. Okay, In will contain 2 to the power of n. I mean, cardinality of In will be 2 to the power of n, but In need not be 1, 2 like that. Okay, so it is just, I mean, it will be out of 3 power n. It is just, we are only taking 2 power n of that. Okay, n such that some In. So here I is set, so I take Jn. Okay, some Ji, where Ji looks like this: I by 3 power n, I plus 1 by 3 power n. It need not happen. It just looks like that. Okay. I am not saying that. Yeah, I am not saying that each I will come like this. Okay. It is just Cn is. I mean, actually, I is in In, where In has this 2 power n. In cardinality is 2 power n. see in each step that Cn is union of 2 power n intervals. I mean, by induction, we can define it by induction. Okay, that's the only thing I have. So Cn is union of 2 power n intervals. Okay, and where each interval looks like this, each subinterval look like that. Okay, then define Cn plus 1. If you have Cn like that, then define Cn plus 1 to be union of I in In. Then this is 3i by 3 power n plus 1. Okay, 3i plus 1 3 power n plus 1 union 3i plus 2 3 power n plus 1 and 3i plus 3 by 3 power n plus 1. Okay, that's all. If Cn looks like this, which is union of I, okay, then Cn plus 1 look like this, which is of course twice that. So it will be the total number of intervals will be 2 power n plus 1. Okay, so this is how it is defined. So once Cn is there, Cn plus 1 can be defined like that. So this definition is clear, I believe. Okay. Now see the Cantor set C. This is Cantor set. C is intersection of Cn. Okay. Okay. First, C is non-empty. Why?
One.
Huh? All the Cn is non-empty. Why?
One is there.
1 is there, 0 is there, the end point of all those intervals are there. You are taking the end points of all those intervals. So it will be infinite. Okay? Because end points, whatever I called it as In, is in C. Okay? N points of In is contained in C. N points of In is in C or contained in C, whatever. Okay? So it's non-empty. Okay? 2, C is of course closed. It's intersection of closed sets, closed. So hence compact, all that. 3, it is uncountable. We want to prove it's uncountable. There are 2 ways of proving it. Okay? C is uncountable. So one way is the following. So you can prove that C is a perfect set and any perfect set is uncountable. It was in the exam and the solution was done in the class. Okay, that is one way of doing. So maybe I will prove that. Okay, C is a perfect set. 3 part of maybe 4, it will follow from that. C is a perfect set. Okay, follows from 4. It's non-empty perfect set. Okay. Huh? Okay. So it's a perfect set. What is a perfect set? Perfect set is something which contains all its whatever we defined as accumulation point. Okay. An accumulation point is, suppose that is, if X is in C, we need to prove B of X epsilon minus this singleton X. You remove this X. Okay. Intersection C is not equal to empty. So this is what we want to prove for it to be a perfect set. This is the perfect set is something where every point is an accumulation point, and this is the definition of accumulation point. Every point is an accumulation point. Okay? And it is closed, so it will contain all accumulation point. We already proved it's closed. Okay, closed set will contain accumulation point is a limit point in particular, but all limit point need not be accumulation point because you can have constant sequence. Okay, so this is a perfect set. So for every X, you take a open ball, some epsilon open ball around that, remove that X, that should intersect with C. Okay, but then this is clear to take n such that 1 by 3 power n is less than epsilon. Okay, then okay, then what? Yeah, So X is in C, X is in JN, X is in, yeah. So that's all. It can be, I mean, X is in Jn for some, for this n. Okay, X is in Jn for some, no, it's not, it should not be n. What was that? I haven't used any, for Jn, I haven't used anything, no? So once again, in this definition, I want to use, I put a top, n in the top, okay? Okay. In this definition, there is no n here. I put a n in the top, okay? Jni. So X is in Jni for some I. Okay. Okay. Now, X minus epsilon, X plus epsilon, okay, intersect with the end point of something, right? So X is in there. So this JIN is of length 1 by 3 power n. Okay, right? Length of this is an interval. I mean, X is 1 by, I have taken 1 by 3 power n. X is in Cn. Okay, I mean Cn for all n, and X is in JIN for some I. Okay, the length of this J and I is 1 by 3 power n. Okay, so this X minus epsilon, X plus epsilon will contain JIN contained in X minus epsilon, X plus epsilon. Okay, huh? Okay, this J and I will be contained in that. Okay, so the end point, if you remove X, at least the end point of this will be there. Okay, point. I mean, if it is one of the endpoint, the other point will be there. Okay, endpoint, the other. I mean, either the endpoint or the other endpoint, something will be there. Okay, isn't it? Whatever, I put it in quotation so that you read whatever. Okay, if X is the endpoint of one interval, then the other endpoint will be there. If it is in the middle, then both endpoint will be there, and the endpoint of all the interval you are going to remove further, that will also be there. Okay, this is going to be infinite anyway. Okay? So, okay, so this proves that it is a perfect set, and this proves that it's uncountable. Okay? Okay. Next, well, there is another way of proving it's uncountable. Okay, this map phi from C to, which way I should write? C to C. Notice X is in C. Okay, it is an intersection of all those Cn, so it will be one of those intervals. Then X is equal to summation AK by 3 power k. 3 power k equal to 0 to, I think it starts from 0 to infinity, and AK is in this set 0 and 2. See?
Equals 1.
K equal to 1. The first, yeah, it will be 0, 2. For this set, it is 0 and 2. 1 will not be there. We are removing it, right? So if you have first, it will be in one of those intervals. Okay, so first one will be there. Then it will be either 0 or 2, 0 or 2. It will be like this. So any X can be written like that, right? Okay, anything can be written like that in the Cantor set. So one thing is, this is what is called the ternary expansion of anything in 0, 1, that will have 0. In the ternary expansion, there are two possibilities. I mean, even in the decimal expansion, a number you can write it like that, right? A1 up to AK, then 0, 0, 0 is the same thing as A1 up to AK minus 1, whatever number up to 1 to 9 minus 1 time 9, 9, 9, 9, 9, you can write it like that. But here that will not occur. If you just think about it, such a possibility will not be there, because up to n k minus 1 thing, they have to be equal. Here, if you add 1, okay, it will become either, if it is 0 or 2, if it is 0, it will become 1. If it is 2, it will become 0, but that something will be added here, but that has to be same. So this is a unique expansion for the Cantor set. Yeah.
Restricted to 0 and 2, it's easy.
Restricted to Cantor set, this expansion is unique. Okay, is unique expansion. Okay. First, there exists an expansion. Second, the only possibility where there may be two expansion is something like this: a1 up to ak, a1 up to ak minus 1, 9. Sorry, not 9, 9. This is for, I mean, I wrote it for not 2, yeah, 2 to 2, yeah, 2 to 2, 2 to 2, something like that. Okay. If you want to change it, then this has to become, I mean, if this, we have to add 1 to here. If it is 0, then that 1 is not allowed. Okay, this will become 1. If it is 2, that will become 0. That means 1 will be added to the earlier one, but the earlier decimal should be same. Okay, because of that, this is the unique one. Okay. Okay. Now define. I mean, this is a topological thing which I don't know whether you have. C from C to the 0 to n. This is the cross product, a countable cross product, 0 2 cross 0 2, because you know finite cross product, infinite cross product. This is just a sequence in zeros and twos, sequence 0 to 2, but you can define a metric on that. Okay, because I mean, since there are two elements that you can define a metric, is actually a metric space, and that will be compact. Okay, you know that. Okay, I mean, there is something called Tikhonov theorem. From that, it will follow, but you can directly prove that also. Okay, it is just a sequence in zeros and one. Okay, I mean, anyway, what? Huh? Yeah, yeah. We need to show it is subjective. No, no, I am saying this is a metric space, this is a metric space, this is a function, and this function is continuous. I have to prove. Why is it continuous? Unless you take the, huh? No, no. If we don't, yeah, yeah. But I want to prove it's a continuous. They are both same metric space. That's what I mean. It's homeomorphic. I want to show that phi is a homeomorphism. Then phi is a homeomorphism. I want to show that. Hmm? There is no metric here. What is the metric here? That has a metric. Then how do you say isometric means? It should preserve the metric here. What is the metric here? What is the metric? P is a homeomorph. Well, let us not take metric and all. This is a topological space in the sense that to define a topological space, you have to define open set. To define open set, you need to define closed set. To define closed set, you need to define what is convergence. Okay, convergence. If you have, so if you want to talk about product topological space, so it is just some sequence converges if and only if it converges in each coordinate. Okay, coordinate wise convergence. Yeah. Huh? Why is? I'm going to prove, explain. Okay. Then phi is a homomorphism. Claim. Okay. It's clearly phi is 1 1 and on 2. I mean, it's well defined. It's well defined because it's unique expansion, and it's 1 1. It's on 2. Everything is clear. Okay. We have to prove that it's continuous. Okay. So why is it continuous? That's because P is locally. So phi n is a map from, to prove phi. I mean, this is a compact topological space, compact T2 topological space. Okay. I have to prove that phi is continuous. That's the only thing I have to prove. No, no, it's a metric space actually. You can define, but I am taking it as a topological space. That's enough. I said that convergence here is coordinate wise convergence. That's all. Okay. some function is continuous if you compose with the coordinate. See, it's a fact that phi some function uh, huh? What continue? Because it's compact, it will follow. Okay, because this is compact, it will follow. Okay, we only have to prove it's continuous. To prove phi is continuous, enough to prove with the topology of coordinate based convergence, it's enough to prove. I mean, you just apply the convergence. I mean, something converges. Enough to prove that pi n of f, pi n of phi is continuous for all n, where pi n defined from 0 to n to whatever. I mean, which is just the, I mean, this is just the number, no, real line or whatever. No, 0 to, okay, it's 0 to. Okay. This is just the coordinate projection, nth coordinate projection. Okay. Now, if you apply pi n of phi, okay, at x, okay, you see that, I mean, n is some number. Okay. After some time, this x, the ternary expansion, okay, pi n of f, pi n of x, I mean, it's constant on a neighborhood, right? X has the sum expansion, then around a neighborhood around that, it has the same expansion up to n. Correct? If x is in one of those j and I, okay, then it will have the, so pi n f is locally constant. Okay. Any locally constant function is continuous. Okay. You can use convergence or you can use inverse of open set or something. Hence continuous. I mean, this we noticed in the last class also. Okay. Hence continuous. Okay. So a Cantor set is actually homeomorphic to this set. I mean, it is onto, it is continuous. So because it's by compactness, inverse is also continuous. So it's homeomorphic. Okay. Okay. Now, sixth one is Cantor set C. You take the n power of that. That is actually homeomorphic to C itself. That is clear, right? That's because 0 to n is actually isomorphic to 0 to n. Right? Clear, right? You just write it in a different way. Okay? It's because of that. So that is the property. You take the infinite product of Cantor set, it is actually homeomorphic to Cantor set itself. Huh? What is?
Set wise, they're equal cardinal.
No. It is just the infinite. I mean, each 0 2, you just have to write that. You just work it out. It will be homeomorphic. Set wise they are equal, but you can define the morphism. It will work. It is just the coordinate wise. It has to converge. Okay, it will work. Okay. Something converges if and only if if you project through the coordinate thing, it converges. So the same thing will work. So fifth or sixth or seventh, I don't know. 0 1 is a continuous image of Cantor set. Okay. Image of Cantor set. There exists a f from C to 0 1 onto continuous. That's all. Okay. So which is just you define f of summation k equal to 1 to infinity ak by 3 power k equal to summation k equal to 1 to infinity ak 0, ak is 0 or 2, right? Yeah, 2k plus 1. Okay. You have to verify this is 1 1. I mean, it's well defined because AKs are well defined, fixed one, so it's well defined. Okay, and no, you need to verify it's continuous. Okay, to verify it's continuous, see, it is just the
If you have a sequence,
yeah, what uniformly converging function. I mean, suppose some xn converges to some x. Okay, xn and x has to be in some interval. Okay, so they will have the same first n thing. So I leave it as an assignment. Okay, I will tell you the proof. Okay, if you have some x, this is some x. Okay, this is assignment. Okay, it has something to prove, so it's assignment. But I tell you the proof. Okay, you take x equal to this. Suppose some xn converges to some x. Okay, then xn has to be very close. You given an epsilon greater than 0, you take some 1 by 3 power n, whatever, 1 by 3 power n less than epsilon, or you want it to happen here, so 1 by 2 power n less than epsilon. Okay, then you take some 1 by 3 power n, which is less than 1 by 3 power m, maybe less than 1 by 2 power n. Okay, so that xn and x will be in the same interval, same that interval. So that means when you take the image, the first an coordinates of this, the image, will be same for both of them. Okay, so by that metric, that if that converges, this will converge. Okay, that's what you have to do. Okay, so this is an assignment. Something you have to write. So this is an assignment. Okay, so that this proves it's a continuous image of that. Okay, but there is something more which I need one class actually. From this you can prove that you can take the power of n. So Cantor set can be taken there. Actually, you can actually prove any compact set is an image of Cantor set, continuous image of Cantor set. Okay, let's not go into that. Okay, so let's see. Huh? Any compact metric space. Sorry, any compact metric space. Okay, if we have time, we will do it. Okay, let's see whether we have time. Okay, the seventh one is what we have missed. C is nowhere dense. It's close. It's nowhere dense. It's nowhere dense means where it, I mean, anything is dense in itself. So nowhere dense in 0, 1. Okay, it's nowhere dense in 0, 1. So that is because if you have a x in C, then you take x minus epsilon, x plus epsilon. That should intersect with the complement. Okay, that's right. So if x in C, then x is in one of those j, n, I. Okay, for some I. So choose 1 by 2 power n is less than epsilon. Okay, then this will intersect with that. Huh?
that same argument.
Same argument. Yeah, this implies x minus epsilon, x plus epsilon will intersect Cn complement. Okay, Cn, so it will intersect C complement, which contains C complement. Okay, okay. Is fine? 3 to the n, yeah. Yeah. So this is nowhere dense, is clear? Nowhere dense means you take any open interval around that should intersect with the complement. Okay, you take it to some as small open set, closed set like that, closed interval, that will intersect with the complement. Okay, because you are going to remove. Okay, this is nowhere dense is clear. What is the other property? It's of course uncountable because any perfect set is uncountable. Yeah, I have said already. Yeah, I have already said, but compact. You don't need compact. So uncountable, closed, compact, nowhere dense. It's this, that. Finally, there is a topological property. C is totally disconnected. Let us see whether I have missed anything else. Totally disconnected. Meaning is the following. Let's define that and then prove it. Okay, let's do it there. This is the definition. A subset or something, it's totally disconnected, or the whole matrix space also. If for x, y in S, x not equal to y, there exists ux with x and uy containing y. This is element of, okay, such that ux intersection uy is empty and ux union uy contains S. I mean, if you take open balls there, otherwise it's a, if you intersect with that, you get the open set in S. It contains S. If a space is said to be disconnected, there are just two non-trivial proper, I mean non-trivial proper open set, which covers the whole set. Okay? But given any 2 points, you can do this. That is what is totally disconnected. But the even rationals, for example, Q contained in R is totally disconnected. Right? Yeah. Of course, there is no point otherwise. Okay, there is ux us open. Okay. So, for example, rationals are disconnected. So, if you have two xy rational, then x is less than y or something, then you find a irrational z between y x. Okay. There z is in R minus Q. Okay. Then you take minus infinity x, minus infinity z equal to ux and minus z infinity equal to uy. This has x and y. This covers the rationals. If you take the intersection, it will open in S. It is open in X only I am taking. Otherwise, I mean, if you take open in S, if you take the intersection, then it will be equal. Okay. Okay. I'm just saying it should contain S. Yeah. Okay. Now, equivalent definition. So, I finished with this. It's equivalent to saying for any x in, I mean, for the C, we want to prove C is totally disconnected. So, for that, for any x in C, there exists a E contained in x minus epsilon, x plus epsilon. Okay. Intersection, yes. Sorry, intersection C. Intersection C, such that E is open set, both closed and open. Okay. It's enough to prove this. Then you take it's both open and closed. So E and E complements are open and they're open sets. So if you have an x and y, there is a distance between them. Okay. You take epsilon to be half of, I mean epsilon to be half of that or something. Okay, then x minus epsilon, like this will contain x. So this set will work for that. This definition will implement for anything. Totally disconnected is equivalent to this. Yeah, yeah. This is for C. Sorry. Yeah, this is for C. Yeah, you are right. This is for C. Yeah. No. Totally disconnected. C is totally disconnected. Okay. This is equivalent to this. Okay. It's enough to prove this. That's what I'm saying. Every epsilon. Yeah. Okay. The equivalence is clear. Shall I write it? That's because, I mean, it's an exercise. Okay. It is just that if you have some x and y, then there is a positive distance between them. You take epsilon less than that. Okay. Then x will be in this set. and y will be outside that. Okay, then this set will contain this. E complement is another open set which will do the job, and E complement will cover C. Okay. So for the Cantor set, okay. So now for x in C, take, I mean, E itself equal to that, x minus epsilon, x plus epsilon. Okay. If you want to, I mean, say here the closed and open set is, I mean, there is no closed and open set containing 0, 1. Okay. I mean, what I mean is closed and open set in C itself, okay, in C. Okay. So you take this itself, x minus epsilon, that intersection, yes. Okay. Then E is open in C. Okay. You have to prove E is closed also in C. Okay. And for sufficiently small, I mean, yeah. So you take, I mean, take let 1 by 3 power n less than epsilon or something. Okay. Now after some time, you will get all the closed ball inside that. I mean, those closed interval inside that, and it is just the intersection of all those closed intervals. Okay, that will be closed. Eh? Sorry, C, 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 C. Sorry. Which middle step? Which middle step? Cn is isomorphic. That's just a statement. Cn is just isomorphic. That will be used to prove that any compact set is image of Cantor set. I mean, you first to prove take 0, 1 is the image of something, then 0, 1 n will be the image of something. Then you can do something, each k you can embed it like Hilbert cube, you can do something. Okay, it's like Hilbert cube. 0 power n is 0, 1 power n is Hilbert cube, right? So anything you can embed in Hilbert cube. Any, yeah, separable metric space you can actually, I mean, you can embed it in Hilbert cube. Okay? It will follow because of that. Okay, totally disconnected, uncountable. Yeah, I think I have done everything. Yeah. Have any questions?